Hey everybody, William O'Bannon here of Stats Whisper, bringing you week 5 of our webinar. Very exciting week this week. We are going multivariate, right? Step 5, multivariate analysis. So let's jump right into that. As always, we want to keep in mind where we are in our 6 steps of data analysis. So we are all the way down toward the bottom this week. And step number 5, the final analysis round, right? So for data analysis, right? This is the final round. Like in you have your significant suitors, and you got to pick one, which is the strongest relationship. And pretty much the same thing with data analysis. In our last step 4, we found out that the dependent variable has a significant relationship with all the independent variables, and we must do this final analysis to find the strongest relationship. Right, so the data analysis. Right, so here you go. You have one central data, 4 suitors, all significant relationships. Which is the strongest? The same with our data analysis. We have 4 independent variables and 1 dependent variable, which is our central construct of study. And we saw last week that it has a significant relationship, right? The dependent variable being the it, with each independent variable via the one-on-one bivariate analysis. So last week we could see the dependent variable had a significant relationship one-on-one with each independent variable, but as we said, what we cannot see is which one it has the strongest relationship with. Now please don't forget, in the bivariate analysis, it didn't matter what structure our dependent variable was in terms of continuous, categorical, right? Because you just had a certain combination of tests. This week, it does matter. So we will be looking at our 3 dependent variables. The first one on this screen being the dependent variable happiness, measured as a continuous variable, 1 to 5, right? Then next, now keep your eye on the dependent variable. Right, there we go. That's the next slide. The only thing that changed was the dependent variable. We're looking at happiness as a categorical variable with 2 categories, meaning, are you happy? Yes, no. Right, so the first one is, how happy are you on a scale of 1 to 5? That's the dependent variable. Here, our dependent variable is, are you happy? Yes, no. Okay? So we'll be solving the first model and this model, and also this model. Right? So our dependent variable here is, are you happy? Yes, no, and somewhat. Right? The old right? Yes, no, and somewhat. And again, we are looking at 3 different, well, three dependent variables that are structured in 3 different ways, because you need to know how to do a test for each of the 3. So if we just looked at one and you encountered like a categorical variable with more than 2 categories and we hadn't gone through that, you might not be able to do it. So we're going to do all 3. The final analysis round. Multivariate analysis. Now what does the multi mean in multivariate analysis? It refers to usually multi meaning many what? Many independent variables. You could say multi-independent variables, right? So we'll be doing an analysis between the dependent variable and multiple independent variables. And for our purposes here, we'll be looking for the significant independent and dependent variable relationships out of all of them, which is the strongest. So in SPSS, to look at our outcomes, we must know how to do 3 separate regression procedures. Linear regression, that's 1. 2, binary logistic regression, that's 2. And 3, multinomial logistic regression. Now, when do we use each? There you go. So you got 1, 2, 3 there. So again, just like the bivariate test, the key to choosing the correct multivariate test is based on the structure of the dependent variable. So we need to consider 3 structures once more. Continuous, right? So we have our happiness measured as a continuous variable. The happiness, yes, no, right? That's a categorical, 2 categories. And our happiness, yes, no, somewhat, which is categorical, 3 or more categories. Now, which test goes with each? So we have the multivariate test key corresponding to the bivariate test key. So in the case of a continuous dependent variable, right, the first one here, the regression test is linear. Then the second line, in the case of a categorical variable with 2 categories, the regression test is binary logistic. And lastly, in the case of a categorical variable with 3 or more categories, you would use the multinomial logistic regression test. And you'll see that's not only the hardest one to pronounce, it's also the most intricate of the 3 too. Maybe that's why they gave it that name. I don't know. So here we go. So we have them plugged in here. So for our happiness on 1 to 5, we're going linear regression. The happiness, yes, no, 2 categories, binary logistic. And the happiness, yes, no, somewhat multinomial logistic, right? Trying to use a little repetition to embed these procedures in your memory. So let us start off with linear regression. Through linear regression, what we're examining is if a significant linear relationship exists between a dependent variable, right, like our happiness continuous, with the independent variable. So to review the linear relationship, right, so here we go. So if you recall, unless this is the first time you're hearing it, right, so we have the XY axis. Now we have happiness on the bottom axis, the X, that goes 1 to 5, right, horizontally. So 1, 2, 3, 4, 5, 5 meaning the most happiness, 1 meaning the least amount of happiness. Then on the Y-axis, on the side, going vertical, we have humor, and that goes from 1, 2, 3, 4, 5, right? The same kind of scale, with 5 meaning the most humor and 1 meaning the least. So each scale goes from 1 to 5, meaning the most happiness and the most humor. So if there were a relationship, a linear relationship between humor and happiness, the points would meet, right? So for example, we see here case 1, right? That little dot there, that's a person. So that person, what did they score for happiness? They scored a 1. And what did that person score for humor? They also scored a 1, therefore indicating that a low amount of humor was associated with a low amount of happiness. Then, going diagonally, you see there's case 2, right? So what did they score? They scored a 2 on happiness, and what did they score on humor? Also a 2, right? So this is some coincidence, right? That they scored ones and twos and threes. And so I kind of structured it that way so it was a little easier to interpret. So anyway, so here we go, 3. So case 3 scored a 3 on happiness, and what they score on humor? A 3, right? So you'll see as each case scores 1 point higher on each scale, on the one scale, they score a point higher on the other scale. So you could say the little spaces are meeting, right? So if you take 3 and go up, right, it meets at 3. 4 and go up, it meets at 4. 5 and go up. So as each person increases on the score of one scale, they're moving up the score on the other scale, and that's making a line. And that's linear regression. That's the line. So there we go. So if we got rid of the labels and we actually put the hypothetical line, which you may have seen before, that's the diagonal line that linear regression is explaining, meaning as the one goes up, the other goes up, and if it went up perfectly, they would make a straight line, or a diagonal line, which is straight but diagonal. Now the fun stuff, SPSS. Because we don't want to just talk about this stuff, right? We want to apply it and do it, right? We don't talk about it and say, why, that's interesting, and then not know how to do it. So let's look at linear regression in SPSS. First, you go to Analyze Regression Linear. We put our dependent variable in the dependent box, the independent variable in independence box. Remember the multicollinearity statistics, and then click OK. So that sounds simple. Let's see if it is. There we go. So we have our SPSS. Go to Analyze, Regression, and Linear. There we go. So we can expand this a little bit and go down, and we want to find level of happiness, right? That's our continuous variable. So that goes our continuous variable, which is also our dependent variable. So that goes in dependent. And then we have our predictors we want to put in our independent variables. Remember, so many bills monthly. Then remember, we had to dummy code the education level. So instead of education level, we have college, yes, no, high school, yes, no, graduate school, yes, no. We leave one out. That makes up a reference group. So we'll leave out graduate school and put in high school. And college, this should sound familiar from the past weeks. Then we want to put in humor and aloofness. Now, as I said, that when we looked at the checks of test assumptions, we want to put in our collinearity statistics. So we go in Statistics and click Collinearity Diagnostics, right, and continue, and OK. So here is our printout, right? So at the very top it says regression. That's how you know where it starts, right? And then variables removed. Now this is what we're going to look at in the slides. 3 boxes right here. We're going to look at the model summary, the ANOVA box, and the coefficients. Right? You'll see in the slides the first thing to look at is right here where it says SIG. That tells you if the test is significant. The third box tells you which predictors are significant. So the model must be significant before you consider individual predictors. So you look at that first, then the predictors. And then lastly, under the model summary, you have your R squared, which tells you how much variance in the dependent variable is explained by the model, meaning the independent variables. So let us go back to our slideshow. As I said, the first thing we want to pay attention to is at ANOVA box. Right, now we saw right on the right-hand side that it said sig 0.000. So that's for the whole model. So it has to be 0.05 or less to be statistically significant, right? So we see it is. So that tells us that the whole model is statistically significant, meaning that we can go on and consider the individual predictors now. If it wasn't, we would just say that it wouldn't be appropriate to look at the predictors at all. Okay, so the first thing we want to know about the predictors is which predictors are statistically significant, right? Which predictors are related to the dependent variable at a statistically significant level. And of course, the probability, which is the sig significance, the probability must be below 0.05. So we see through little arrows, right? The first one, many bills monthly, is below 0.05, right? The high school and college education is not statistically significant, right? So we don't consider that, but humor is significantly related to happiness. So we have many bills monthly is related to happiness, and humor is related to happiness, and your level of aloofness is also significantly related to your level of happiness. So we have 3 significant predictors in the model. Then the next thing we want to look at is, yes, they're related significantly, but are they related in a positive or negative way, i.e. the directionality, right? So they could be significantly related, but does that cause one to go up together, or one goes up and the other goes down, right? So many bills monthly, we see there is a minus sign, right? So right, the beta, the B, that's negative 0.45, meaning there's a negative relationship between having many bills monthly and your level of happiness. So if you have many bills monthly, then your level of happiness goes down. Then humor, we see down there more toward the bottom, second from the bottom, the beta is positive. It's positive 0.297, meaning as humor goes up, happiness goes up. And then lastly, for aloofness, it's a negative 0.186, meaning as aloofness goes up, your happiness goes down. Now, don't forget, we wanted to see what was which variable had the strongest relationship, right, with the dependent variable. So not just significant, but which is the strongest. Now, the standardized beta coefficient indicates the strongest predictor in the model. In other words, which independent variable predicted the dependent variable the strongest. And we could see the highest one, so many bills monthly is negative 0.304. Negative doesn't matter. It's the size of the coefficient. So 0.304. Aloofness is negative 0.242, but humor is 0.441. So that's the highest. So it has the highest value, meaning that humor was the strongest predictor in the model of happiness. So there's our answer, right? A big process following all those data entry and preparation of data, right? Following everything on down to bivariate, multivariate. That's our answer. It's humor. Now, before we go to the stating it formally, let's just look at that R squared really fast and discuss what it is. So you'll remember in that model, the R squared, I said, explains the variance in the dependent variable. Variance meaning the scores go up and down. So you could just look at it like life. What makes your happiness go up and down? Could be the weather, could be a good meal, All sorts of things make your happiness go up and down. The same in the SPSS with the measurement of happiness, right? The scores go from 1 to 5. And we want to explain what makes those scores go up and down. So there's a certain amount of variance that goes up to 1.0, right? That's 100% of the variance. That explains the scores in happiness going up and down. Now the R squared is 0.4489, meaning almost 50%, right? So 0.5 would be 50%, almost 50% or half of the variance in the dependent variable happiness, meaning half of the reasons it goes up and down are explained by our model being our independent variables. So what it's saying is that almost 50% of the variance in happiness is explained by the independent variables in our model. And that's actually a very high R squared. Usually it doesn't get much higher than 50%. It could even be 6% or 7%, and the model can still be significant. So 50% is a very big R squared. So if we were going to state the results of our linear regression, we might say the multivariate model indicated that the independent variable humor was the strongest predictor of levels of happiness. And then we put the standardized beta in parentheses. All right, so the first one is down. Now the next one, binary logistic regression. Remember, that tells us if there's a significant relationship between a categorical dependent variable with two categories and the independent variable. Now in SPSS, it's much the same procedure. Analyze regression, but instead you go to binary logistic. We'll put in the dependent variable in the dependence box and the independent variables in the covariance box. Now always under options, click the 95% confidence interval, right? It'll say 95% CI of EXPB. That's exponent beta, that's the odds ratio. So whenever you publish or write up your results for a logistic regression, you'll put the odds ratio, but always the confidence intervals too. It's just standard, right? Then we click continue and OK. So let's give that a try. So analyze, then regression, and binary logistic, right? Just like it said. Stretch it out. Now we got to find what? Happiness, two categories, yes, no. Right. Is study participant happy? Yes, no. So happiness YN goes there. Again, we will put our education. Well, first many bills monthly. Then our education, first high school, then college, then humor, then aloofness. Now what? Confidence interval. So under options, click that. And then right here where it says click the CI for exponent beta, EXPB, 95%, right? That's the 95% confidence interval. What that says is, you know, we don't think we have the actual odds ratio in the population, but it'll give us an interval, and it'll say we're 95% confident that we might not have the exact one, but it falls within this interval. We'll look when we get the results. So continue, then OK. So there we go, logistic regression. Right, so 2 boxes of supreme interest in this printout. So we have the case processing summary. It says how many cases are included, right? Now what we really want to look at first is that omnibus test. So go down a little. There it is. The omnibus test of model coefficients, because where it says model and sig, where it meets here, that's the significance level of the model. So if it's significant, you can look at the predictors. If the model is not significant, you don't need to consider the model anymore, right? So the model is significant. So the next box to refer to is the last box right here, the variables in the equation. So these two boxes are in our slides. Let us reference that. Okay. So here's that omnibus test that I was So again, we see that first thing we look at is if the overall model is statistically significant, right? So 0.000 is below 0.05. So we say, yes, it is. Let us move on to the predictors. So this is that bottom box, right, in the printout. These are the predictors of happy, being happy, yes, no, right? So we look at the statistical significance of the predictors, and we see there's one statistically significant predictor. Some of the others are close to 0.05, like humor, but they're a little above. So if you're going to set it at 0.05, 0.05 it is. So 0.059 is above that, so a little above the cutoff. So many bills monthly is the only significant predictor of happiness. Yes, no. Now we want to look at the directionality, right? So significantly related, but does having bills explain having more or less happiness? So if it's negative, we know having many bills monthly, right? Yes, equals less happiness, right? Because there's a minus there. Also, we see the odds ratio is less than 1, right? So we look at the odds ratio next, and it's less than 1. So whenever there's a negative relationship, right, the odds ratio is going to be less than 1. If it was positively related to happiness, the odds ratio would be greater than 1. So we look at the odds ratio. It's not very interpretable because this is the one where it's 2 times more likely to happen, 3 times more likely to happen. But when it's negative and it's below 1, you can't really communicate it like that. So you need to convert it. Now you convert the negative odds ratio by dividing 1 by the odds ratio. So the odds ratio is 0.097. So we divide 1 by 0.097, and that comes out to 10.31. Right? So 10 times, right? So there's our communicable odds ratio, 10 times, a little over 10 times. So we would state those with many bills monthly are over 10 times, right? The odds ratio 10.31, less likely to report being happy relative to those without many bills monthly. Right. So that will make intuitive sense to a lot of people out there. All right. The last regression model, multinomial logistic regression. This, like I said, this one's a little more sophisticated. I was doing analysis for years, statistical that is, for years and years before I ever did my first multinomial logistic regression. So you're way ahead of the curve on this one. Okay, so it tells us if there's a significant relationship between a dependent variable with 3 or more categories with the independent variable. Okay, the same sort of pattern in SPSS. Analyze regression. We go to multinomial logistic. Now here's a little difference. You put the dependent variable in the dependent box, but you put the categorical independent variables in the factors box and the continuous independent variable in the covariates box and click OK. Now this gives you the 95% confidence interval by default. so you don't have to click it. So let's go to SPSS. And so we go to Analyze, Regression, then all the way down to Multinomial Logistic. There we go. Stretch that out. Now we go to the bottom, and we have our happiness, Y&S. Yes, no, sometimes. So is study participant happy? Yes, no, somewhat. Rather, not sometimes, somewhat. We take that, we put it in the dependent box, and then you can select the reference category. But here's the trick. Since you have more than 2 categories, there's a reference category within the dependent variable. So you can say you open reference category, you could select the last category, the first, or pick anyone in between. So by default, it picks the last, which is fine with us. That's the happy yes. So you'll see in the interpretation what I mean about the reference category within the dependent variable. Okay, so we put our mini bills monthly. And this gets a little convoluted, so let's leave out education this time because it's just another categorical variable. It's not significantly related anyway. And then we put in humor and aloofness. Whoop, remember what I said. the continuous go in the covariates, right? So aloofness and happiness are continuous, measured on a scale of 1 to 5, with higher meaning more humor, higher meaning more aloofness, right? And then we have our factor, many bills monthly, yes, no, categorical, in the factors list. Then we click OK. So here we go. Nominal regression. Okay, if you want to call it that, that's fine, right? We have our case processing summary. Now we want to see that first box, just like in binary logistic, that tells us if the model is significant. Right, we got to go down a little bit. Right there it is. The model fitting information, you can see on the far right, significant 0.000. So the significant model, and then we want to look again at the last box, the parameter estimates. Those are the individual independent variables predicting happy, yes, no, or somewhat. Okay, so the 2 boxes. Let's look at them a little blown up on the slides. So, like I said, the model fitting information, the far right corner, significance 0.00. So the model is overall statistically significant. First thing we look at. Next, we look at the statistical significance, second, of the individual predictors. Now you'll see there's 2 boxes, right? Now look at A underneath the box. It says the reference category is yes. So what that's saying is you're getting results for each category within the dependent variable, and it's referring to the other category in the dependent variable. So there's 3 categories, yes, no, and sometimes. Right? So the reference category is yes, and the ones we're looking at are the categories no and sometimes. So they're going to tell us the outcome, their outcomes relative to those that indicated, yes, I am happy. So that's a little more simple if I actually point it out. So you can see here in the no, right, the top one's no, the significance level is 0.006. So that's the statistically significant finding, right, in this box. And it's for humor. And when you look at the beta for humor, right, the B, there's a negative, right, negative 1.66. So that means negative meaning less. So what it's saying is, in reference to the reference category, yes, people who are happy, yes, people who indicate no, as in, no, I'm not happy, have significantly less levels of humor. They have less humor, right? And then the same thing with the sometimes category down below. You'll see humor is also statistically significant, 0.026, right? And humor, and there's a negative beta, right, which we're going to address again on the next slide, but twice is good for this multinomial logistic regression. That takes a minute to sink in sometimes, right? So less. So in reference to those who are happy, yes, those are happy sometimes have significantly less levels of humor, right? So there, like I said, there we go again, right? So take one good look at it, right? So in reference to those who say they are happy, yes, right? The negative beta, negative 1.66, right? Those who are happy, no, has significantly, right, 0.06, significantly less, minus 1.66, the minus meaning less humor. And then the same thing with the sometimes category. We have the minus 1.18, indicating less. So in reference to those who are happy, yes. Those who are happy sometimes or somewhat, right, have significantly less level of humor. Now here's a little trick here, me being tricky. So then we look at the odds ratios, right? So you need to remember this. Whenever you have a continuous variable, the odds ratios are not interpreted the same times as if it's categorical, right? So if we have an odds ratio like the many bills monthly and it's 10, they're 10 times more likely or less likely to be happy, right? Well, you don't interpret the odds ratio of a continuous independent variable like humor or aloofness the same way you would of a categorical independent variable. So you could note the odds ratio in your description, but you wouldn't say this many times more or less likely because it's a continuous independent variable. Right? So I say it again, right? You don't interpret the results the same way for a continuous independent variable as you would for a categorical independent variable in a logistic regression model. So how would we state our findings? We would say, in reference to those who are happy, that's the yes category, those who are not happy, the no category, and sometimes happy, have significantly less levels of humor, and that's what our model indicated. All right, the good news is that the multivariate analysis, step 5, is now complete. Now you have seen how to do regression tests looking at all 3 variable structures, meaning linear for continuous, binary logistic for categorical with 2 categories, and multinomial for categorical outcomes with 3 or more categories. You don't see many multinomial logistic regression models, but just a passing familiarity with them is just a world's difference than no idea about them. So we've gone over them, and then there's a growing knowledge from there. Okay. That's great, everyone. Thanks. I'll see you at the next webinar.